So what we're saying is that in an example like this, there's a couple of approaches that we can take. I have taught you sort of the informal, the shortcut, we might say, of, quote, can you see it? Wherein we start at the base, we swoop our way around, and we finish with the argument of the logarithm. So in this way, I would be saying 4 to the power of 10 equals 16 to the power of x. Now, the sort of the drawback here is you look at 4 to the 10th and you're like, oh, I don't know what 4 to the 10th is. Well, that doesn't really matter. Okay, we want to try to make the bases the same here so that we can equate the exponents. And I look at 4 and 16 and I think, oh, we could do that quite easily. We can say that 16 is the same thing as 4 squared. So if it's 16 to the x, then over here on the right, it's 4 to the 2 to the x, which we also know is what? 4 to the 2 to the x is the same thing as, don't go back up. Just say 4 to the 2x. When we have a power of a power, we do what with those exponents? We multiply the two of them. So I'm going to actually save a little room and we'll just write 2x right there. So 4 to the 2x. And then we can equate those exponents. We can say, well, look, if 4 to the 10 equals 4 to the 2x, then 10 must equal 2x. In other words, x must equal 5. And we got our result that way. Okay? Now that's one way of considering the problem. That's one way of looking at it. Okay? Another way, and perhaps why I want to introduce this, or introduce class with this example rather, is because we have learned this new property that we've called the inverse property of logarithms. And the way that the inverse property of logarithms works, remember, is that we say, hey, look, if you've got log base b of b to the x, that equals x. Okay? In other words, if we have the common log of 10 to the x, it's x. Or the natural log of e to the x, it's x. Or log base 2 of 2 to the x, it's x. Anytime those two bases are the same, that's like saying, here you go, Mossy, plus 5 minus 5. Or Alex, times 2 divided by 2. Or Grove, take the square root and square. These are inverse whats? They're inverse operations. And so what I look at over here, and we'll work this out, we'll do it in green, is I see log base 4 of that 4 to the 2x. Remember, we're changing 16 to 4 squared. And I see that equaling 10, and then all of a sudden I can say, oh, look, those two cancel out because of the inverse property of logarithms. That's like saying, oh, he is squaring a square root. Those undo each other. And the left-hand side, we're just boiling down to 2x. And therefore, x equals 5. And we get our answer much quicker that way. So don't be locked in to say, I'm always going to do the can you see it approach. Be versatile. That's like saying, I'm always going to solve every quadratic with the quadratic formula. Right? Does the quadratic formula work every time? Sure it does. But it might not be the most efficient way of solving a quadratic, let's say. Can you see it is a great illustration of how you can change a logarithm from log form to exponent form, but it's not always the best approach. Okay? Let us, okay, so up there in orange, inverse property of logarithms. Here's what I want to do. Take a little sidebar here, and I want to consider another example here. Let's practice using that inverse property of logarithms. We're going to say 2 to the x equals 7. 2 to the x equals 7. Okay? Now, I don't want you to do the can you see it approach, because the can you see it approach I feel like we're pretty good at right now. I want you to practice using the inverse property of logarithms, which means I need to perform a particular operation on the left side of my equation and do that same operation on the right side of my equation. Now, it wouldn't make sense for me to say, hey, let's times both sides by 3. Nate, could I do that legally? Absolutely. But would that help at all? No, that'd be stupid. You'd be like, dude, why are you doing that? I could take the 5th root of both sides legally, right? I can do that to both sides. I'll do what I want as long as I keep it balanced. Whatever you do on the left, you do on the right. However, that ain't going to help our cause. What do you want to do to both sides? Joey, take the log of both sides. Make both sides, let me scooch this 7 over. Make both sides the argument of your logarithm. So we can say log of the left and log of the right. Now, as it stands right here, did I do what Joey said? Somebody back there that heard him, shake your head. Yeah, that's right. Jack, why didn't I do what Joey said? What did he say do? All right, so yeah, this is an implied base of what, class? 10. So I took the what kind of log of both sides? Common log. And that's not going to help me any. That's not going to help me any. I want to take log base 2 of both sides. So I take log base 2 of the left and log base 2 of the right. Now we're cooking with peanut oil. Now those two guys, they're inverse operations. That's like saying, here you go, Drew, times 3 divided by 3. Those undo each other. And from the inverse property of logs, we're left with the left-hand side just being x and log base 2 of 7. Could we have gotten there using the can you see it approach? Absolutely. But we want to be versatile. We want to be able to use more. Are y'all done? Right? Good. We want to be able to use more than one technique or approach. All right, let's ratchet it up a little bit harder. Okay, so here we're going to have the common log of x equals the natural log of 7. Now, can I say x equals 7, Quentin? I got log of x equals log of 7. Why not? Very good. If you didn't hear that, he's correct. He said 1 is the common log, which has an implied base of 10, and 1 is the natural log, which has an implied base of thereabouts. Which letter we use? E. Who's that named after? Euler. Very good. It's called the natural base. Y'all are learning all kinds of goodies. All right. So I can't just simply say, hey, log on the left, log on the right. Let the arguments be equal to, because the bases are not the same. That's like saying 2 to the x equals 3 to the y. X don't equal y. Okay? However, trying to get x by itself, and yeah, I could do the can you see it approach, right? But in this case, I want to illustrate the inverse property of logarithms in a bit of a different form. Earlier, I wrote log base, in orange, log base b of b to the x equals x. Here, I'm going to write it in the second way, which is to say b to the power of log base b of x equals x. That's like, instead of saying times 3 divide by 3, that's like saying divide by 3 times 3. Well, they're still inverse operations. The order in which you do them doesn't matter. They still cancel each other out. That's like saying square a square root or square root a square. They're both going to cancel out. So in this case, what I can do to both sides is I can raise both sides up and make both sides an exponent, right? And I want to pick the appropriate base. So like if I picked the base of e, this would not be a good idea. If I picked the base of e and said, let's make the left-hand side be the power that we're raising e to, and the right-hand side the power that we're raising e to. Reed, would that simplify out either of those sides? Just the right, great observation, just the right-hand side. Class, what would the right-hand side simplify down to? 7. That don't help me. I got 7 by itself. Okay, big fat hairy deal. I didn't want to get 7 by itself. I wanted to get x by itself. So what would you adjust about how I wrote that up? George, what would you change? Very good. So we changed the e to a 10, and now, oh mama, now what happens on that left-hand side, Joe? Good, because there's an implied base of 10 there. Those two cancel out, and we got x equals 10 to the power of natural log of 7. What is the natural log of 7 in its essence? What is it? Like if you were going to say in its nature. It is a what? What's the natural log of 7? Is it an unknown? Is it a variable that changes? It is a number. The natural, like if I whipped out my calculator and said natural log 7, enter, it's going to give me some number. I don't know what that number is, but it is a number. And this is just like saying 10 to some number. 10 to the whatever that number is. That's what x equals. Don't be afraid to express numbers in your math classes in non-traditional ways, right? Like this is a non-traditional. Like if I told my dad, "Hey, Dad, I need to borrow some money," let's say. I need to borrow. He said, "Okay, son, how much do you need?" I need to borrow 10 to the power of natural log of 7. He's going to look at me like you are speaking Greek, son. What the heck are you even asking for? All right, but is that still a number? Sure it is. Okay, so bear that in mind. Do you guys want to try one? Here, let's try this. Yeah, we'll do that. So I know you can do the can you see it approach, but I want y'all to practice using the. By the way, sorry, I left out some parentheses. There you go. Using the inverse property of logarithms. So this is the log base 3 of quantity x plus 2 equals 5. Do something to both sides of the equation such that we get x by itself. Right now, x is being operated upon. We want to find the inverse of that operation so that we can isolate x. Think about what you want to do to both sides. Jake, you got an idea of what we want to do to both sides?
I wanted to set the base to 3 and put that as the exponent. Log base 3.
Fabulous.
This was 2.
3 to the log base 3 of x plus 2. In class, whatever I do on the left, I got to do the same thing on the right. So the right-hand side is going to be 3 to the power of 5. Okay? Now, 3 to the power of 5, I believe, is 243. But even if I didn't know that, what is 3 to the 5th? It is just it's just a number. Just a number. Now, the right-hand side being just a number, the left-hand side now is what? X plus 2. Now, if I said x plus 2 equals like 11, you guys would be in hog heaven. You would just be like, oh, x equals 9. Subtract 2 from both sides. We can do the same thing here. Subtracting 2 from both sides, we end up with x equals 3 to the 5th minus 2, which I happen to know is, or I happen to think is 241. I think 3 to the 5th is 243. Let's double check. 3 to the power of 5 equals 243. Minus 2 is 241. All right. So how would can you see it have differed in this case? Well, if I did the can you see it approach, I would have jumped right on in there and had 3 to the 5th equals x plus 2, which is right down there. So the can you see it approach can help me shave off a step in the process sometimes, like where I don't have to, like Jake told me, raise both sides up as the power and make 3 your base. I can skip that step with the can you see it approach, okay, and that's fine. But in other cases, so we mentioned where were we? That one. As we mentioned a moment ago, sometimes the can you see it approach maybe makes things just a wee bit tougher. So it varies. It depends. All right. Any questions so far about logarithms? We're almost done. We're almost done with logs. I know. I can sense your frustration, your angst, your sadness. All right. Here's an example for you guys to start chewing on. I will remind you as you begin looking at this, that we've talked about there are 2 steps. Count them, 1, 2. There are 2 steps for finding the inverse of a function. Lewis, do you remember those 2 steps? We talked about them in section 10.1 and 10.2. What are the 2 steps for finding the inverse of a function? Notice my hands. What am I doing? 2 steps. And then solve for y. Good. So remember, if you have forgotten, remember it's switch x and y, solve for the new y. All right, so I want us to do that right here. And just recall to mind, fellas, that f of x is the same thing as what? Y equals. Okay, so good. So y equals 2 times e to the x minus 1. I would like you to tell me what the inverse function is. I'm going to go grab some water real quick, and I'll be right back. Nothing like some fresh H2O to get you going in the morning. While my wife was out of town, my kids and I spent Thursday night and Friday night at my parents' house. And we woke up Saturday morning and had some cinnamon rolls. Do y'all ever do cinnamon rolls? My mom found this local person who makes cinnamon rolls, so she bought 2 pans of them. And we only ate one of them, so she gave us the other pan to take home. I had one this morning, microwaved it a little bit, 15 seconds, no more, no less. And it was divine. Love me some cinnamon rolls. Hey, Luke, you got an answer? All right, so let's start there. So we got x equals 2e to the y minus 1. Now, we got ourselves an onion right here, okay? So Luke has done step number 1. Now I need to peel back the layers. Andrew, what's the first layer that you want to peel back?
Add 1.
Oh, you could add 1, but you'd be wrong in doing so. Jack McBee.
Divide by 2.
Let's take care of that 2 first. Let's divide both sides by 2. So we got, actually, you know what? Let's do this. Insert space. Whoop, get down there. All right. So we'll divide both sides by 2. So we got x over 2 equals e to the y minus 1. All right. Now, let's see, James, what would you like to do next? Take the natural log of what, young man? Let me remind you that we did something. Did we do something similar? No, we did exponents. Aha, aha. We had, initially, this one was 2 to the x equals 7. Of both sides. Well done. Okay, so why did he pick, Alex Cano, why did he pick the natural log? He said, I'll put it in orange to emphasize, he said, take the natural log of the left side and of the right side. Why did he pick natural log? Because of the e. Natural log is the logarithm whose implied base is what, class? E. So this over here on the right hand side is like saying log base e of e to the b, and that's going to equal b. Okay, it's going to cancel out, whatever that is. So those 2 operators undo each other, and Will Edwards, we're left with what on the right hand side? That's the left hand side. Good. So we just got y minus 1. Now let's talk to me a little bit about that natural log of x minus 2. Warning, trick question. Warning, trick question. Talk to me a little bit about that natural log of x over 2. Is that's just a number, right? Would you have said no if I had not warned you? We just got through jibber-jabbering about natural log is just a number, just a number. What makes this not just a number? It has a variable. And that's okay, right? This is not just a number. It's a function. But that's what we're looking for to begin with. Now, Andrew Jago, add 1 to both sides. Good. So what we did was we peeled back the layers. We started on the outside, and we worked our way to the inside. So we'll add 1 to both sides. We get y equals natural log of x over 2, and then plus 1. So that is my inverse function. So here I've got 2 times e to the x minus 1. And then here I've got its inverse, natural log of x over 2, and then plus 1. All right? Now, fellas, let's take a trip down memory lane, and let's see if we can remember what kind of, because it says domain and range, right? What kind of function is f here? What kind of function do we call it when we've got our variable in the exponent? And by the way, what is e again, numerically speaking? About 2.71. So our base is greater than 1, and we got our variable in the exponent. What kind of function is that? Call it out if you think of it. Louder. Exponential what? How do you know it's growth? Because the base is greater than 1. This is an example of exponential growth. All right? Oh, that was crappy. Let me try that again. Good. That's exponential growth, generally speaking. Okay? I didn't do any kind of fancy, like X and Y table. I didn't plot any points or anything like that. But we know, generally speaking, exponential growth looks like that. What do you think the inverse function will therefore look like? That's a hard question. You haven't done much graphing of logarithms. That's really like an Algebra 2 topic for sure. Let me ask you the question a little bit differently then. Oh, okay, go ahead, Katie. Got it. All right, good guess. It won't be exponential decay. James? Say that again. It's good. Yeah, well done. What kind of asymptote do we have over here on the function? The x-axis. It's a horizontal line. That's our asymptote. So when Lewis tells us to switch x and y, what does that mean that this graph will have asymptotically? The y-axis, it's a vertical line. That will be my vertical asymptote. Okay? And talk to me about the domain and the range of this function. The domain here is all real numbers. And the range of my function is y has to be greater than 0. Okay, we can tell that from the graph. We know that from our general understanding of functions. You can raise e to whatever power you'd like. There's no restrictions on the input, and you're only going to get out things that are greater than 0 because you can't raise e to a number and expect to get a negative result, right? So this is the domain and the range of our function. How does that impact or affect the domain and range of my inverse function over here? Read. Is a member of the set. And that fleshes out nicely with our picture, right? Because look over here. Where does the curve exist? Everywhere to the right of the y-axis. In other words, everywhere where x is greater than 0. And then the range, it goes all the way down. I think just like James said, it goes all the way up. Now it's going to start going to the right a lot faster than it's going up, but it's still creeping up infinitely. I can get my car a mile down the road, and I could go up high enough and find it. It's still climbing, okay? Now, couple comments to make, and then the lesson will be yours. Comment number 1, we'll key in on what Reed just noticed. We'll remind ourselves that, fellas, for a function and its inverse, the domain and the range do what? They switch or flip. The domain of my function becomes the range of my inverse and vice versa. Okay, so that's comment number one. Comment number two is that over here with consequently from my first comment, comment number two is that the domain of my logarithm function is restricted. I am not allowed to take the log of a non-positive number. I can't take the log of 0. I can't take the log of some negative number because of the domain restriction that's in place, because of the range restriction of the original function. So because the exponential function has a range restriction, its inverse, the logarithm function, by definition, will have a domain restriction. And therefore, you're never allowed to take the log of a negative number. Okay? And I think we saw that back in our warm-ups for this yeah. No, we didn't. Shucks, where is it? Yeah, right there. We saw this in a previous example, that you're not allowed to take the log of a negative number. So anytime I see something like what's highlighted in yellow there, I got to throw on the brakes and say, whoa, second here, boss. Can't do it. All right. You guys have any questions over today's lesson? Well, y'all were some rock stars. You did a fabulous job as usual. And what we'll do is we'll pick up with our last log lesson tomorrow. And then we'll talk about some end-of-year stuff. Thank you very much. Hope you have a great day. Live Jesus in our hearts. All right, guys. I'll see y'all tomorrow.